Welcome to EHANCE, an AEC podcast, where we learn the why behind AEC professionals so that you can learn your why.
Okay, so you've got some technical questions for me, I guess, next. You've written those out. I guess I printed them out for you. Did you want to hit me up?
Yeah.
So just as a, I guess, introduction for the video, so we're just jumping into this, some technical questions you have about, and Jay Fraser is with Fraser Construction, and so we're just going over, I guess, some, structural engineering questions you might have.
I did a construction management degree, and what we learn, I call it, structural engineering light, like Bud Light. I don't go nearly as deep as you are. There's some things that I didn't really even learn in school. I'm trying to learn them here on the job. One of that is all the codes and loads section. You see it often on the first page of the structural sheets, first page of the architectural sheets.
Sure.
And Fraser Construction reps Butler Pre-engineered metal buildings, which has a now released omni design software. You got to enter in a lot of the codes and loads things. So I'm going to ask you some questions so I can understand what all that is even better. So what does the codes and loads mean, in structural engineering, especially in hurricane prone areas?
So codes and loads, I don't know where that terminology came from because really we just call it design criteria.
Okay.
So we're, engineers are like, I guess a little nerdy, but we call it design criteria. But like this is a job you working on right now.
Okay.
So Compass Commons in Bluffton, May River, South Carolina. But so these are the codes and loads here, and the building code, the IBC, dictates what should be on the plans. So and we talked about it on our podcast, which is ASCE dictates the design loads, and that whole book there. So this is the this is the IRC. I just grabbed a couple books here, but IBC is somewhere. Here's the IBC here. So the IBC, here's the IBC. That book. This is the 18 version, and then this is the ASCE 7 right here. So this is what we have to follow just for loads. These two books, but the good thing is, so there's two references to use. One is the ATC, which I think you have, right? You have access to.
Yeah, that it's a free website. I've gotten good at dropping in a map pen on the project site, and you click a button, it'll tell you what that area's wind speed is and seismic. Wind speed, I guess. That number usually is good to go. Seismic is the preliminary number until the geotech bores, and then it's overruled, right?
Well, so the code allows you to select D as default. Seismic. So you have site class, and then seismic design category. Site class is the soil that's on site, and you can have an A through, I think, D. A, B, C, or D, and it might be worse than that.
The soil, and that's like, is it anywhere from rock to loose sand?
Yeah,
so it's somewhere in between.
Right, and so what happens is the soil interacts with the earthquake for two ways. One is the way the seismic activity propagates through the soil is part of the issue, and then how the building reacts to the soil. That's a different issue. But really what the primary thing with regard to the seismic design category is how the earthquake propagates through the soil. So that's where, because if you think about like a wave that's traveling, like a noise wave even, and it's traveling through water and it hits the air and it hits it differently, right? It's the same kind of thing. So the earthquake waves travel, the motion travels differently through the soil, like from where the earthquake epicenter is. That energy travels differently through soft soils as hard soils. And then when it hits, like let's say it travels, and this is why Beaufort County is such a bad area, okay? Because Charleston is the epicenter of earthquake activity. There is no fault in Charleston, by the way.
Huh.
So
what do you call that? Like,
I went to
a weird spot? Is there a term?
So I went to a seminar, it's been about 15 years ago, and this guy was a geologist.
Epicenter, but not a fault.
He said it's an epicenter, but it's not a fault. And if you look at it on a map, there is definitely an epicenter, but there's no quote unquote fault. And so,
Like
how it,
faults or lines, like something
yeah,
slips.
2 rocks.
Okay.
Yeah. So like California has fault lines. We don't really know what causes it. He just says the geologist was just saying, like, basically there's pressure buildup that's happening there. And we really just had the one Charleston earthquake in the 1800s, the late 1800s. But it propagates through that soil, and then it hits a certain type of soil here, and then it does something different. So it's kind of like that thing I was saying about going through water and then air.
Okay.
Like, how does that work? So that's what the site class is, and it helps dictate what the seismic design category is. And in this area, it's either a C or a D usually, but sometimes meaning seismic design category C or seismic design category D, and it depends on your site class, and it also depends on how close you are to that epicenter.
Okay.
So the closer you are, so northern Beaufort County is a little closer to Charleston, southern Beaufort County is further. So southern Beaufort County oftentimes it's right about 278 actually, Highway 278, where if everything's equal, meaning site class D, northern is usually going to be a D, southern is often going to be a C, seismic design category.
Does Savannah get off the hook for seismic? Does like the Savannah River
Yeah, I mean,
breaks up the
well,
earthquake wave?
It's not really because of that. It's just further away.
Okay.
And so if you look at it, it's that like almost like a topo map as you get further and further away from Charleston. So obviously the building code, going back to your question about codes and loads, I mean, pretty much the building code says what has to be on the plans in terms of the information. And so it tells you got to have wind speed, you got to have, seismic site class, S1-07, which you have in your questions. And all those things have to be listed out specifically. And there's a section in chapter 16 that tells you exactly what you have to have. But I was mentioning the ATC. That's one resource. Unfortunately, the ATC is going away, that website. But fortunately, the good news is ASCE is picking it up. It's picking it up, and it's going to be a free version. And actually, we've started using that internally for our resources, and we found that it was a little bit of a shift for us, but we found that ASCE actually has some better things.
Concur, yeah.
Yeah, it has some aspects of it. It's got snow loads and things that the ATC, and also it sort of puts it all together for you. And it's free, so anybody listening to this can just use that, and you can type in the either the address or the lat and the long, and it'll just populate that data for you. So that's pretty much how you get all the design criteria. And I think the term codes and loads might have been a building department or
comes from the layman construction world.
Yeah. So does that answer that question?
Yeah. For seismic, I got some wind enclosure questions for you.
Okay.
There's wind exposure A, B, and C. That's basically, are you surrounded by pine trees and urban blocks? That's A, right?
Yeah. So
and C is you're on the open sea, and B is average.
Yeah. So the building code pretty much says C is default.
Okay.
So you have two aspects of it. Number one is there's a term called surface roughness.
Okay.
Actually, so that's not something that you would normally need to deal with, except you need to know what your surface roughness is in order to determine what the exposure is. And so the surface roughness is the same, but surface roughness is an infinitesimally small thing. So in other words, I think about like the if I had it on grid paper and I was looking at a 1 foot square, then this square would be a surface roughness C.
Okay.
Because it's either grass or water. And the next square over might be a B, right? The next foot square might be a B because it's a tree, and then the next one over might be a D because it's D has a specific criteria. A and D are very special. Yeah. So A is like urban and D is ocean. But B and C are pretty clear cut. B is surface roughness is suburban, so like houses that are closely spaced apart, and also trees. Yeah. So if you think about it, what it's trying to do with the code is say it's rough, and the wind would be broken up by those irregularities. Whereas C is grasslands,
Yeah.
effectively, and then D is like ocean.
Yeah, like right against like this side of this building might be D going that way.
Well, you have to have at least so there's a special criteria for it because you could have a river that was C, but
Yep.
you might have a river that's also D, and I'll explain. So it has to do with the surface roughness. So you have to know what your surface roughness is. It's either B or C, and then from there you can determine your exposure. So a surface roughness B that extends for 1,500 or more feet beyond the building, for I think 30 feet or less, is a exposure B, or vice versa. If you don't have that coverage around the building, then you're a C. So that's basically a quick answer to it. So you have to look at what we do is we actually go in and create a little radius around the building every time, and we put that in the file, and we go a 1,500-foot radius around that building, and if it's got the trees and the buildings around it, then it's a B, and if it doesn't, and you have to look at the full radius, because if you had a quadrant or like a sector that had a high wind, like had a high C, then that wind could come in that sector and be a C exposure. So that's a bit of a summary of that. So the best way to do it, we actually go into Google Maps and do the distance measure and do from the building out 1,500 feet, and then kind of like draw a circle around that. And then we look at that and say, how much surface roughness do we have around it? Is it mostly B or is it mostly C?
I thought you guys just went, yeah, that's a lot of pine trees over there.
Yeah. No, we actually have a procedure that we have for doing that.
Okay.
And that's the long and short of it. Is every job we have a Google map that we go in and do that little diagram, and we also, every job we have an ASCE file and we put that into the file.
Last question on the codes is the wind enclosure. Is it easier, or what's the hardest for you to design? A building with a roof and 4 walls, a building with a roof and no walls, or a building with a roof and some partial walls and soffits and things?
Well, that's an interesting question. I mean, are you saying about the enclosure category, or are you saying like difficulty level?
The enclosures create uplift, and then you got to design the holding down to all that uplift.
Yeah.
So I don't know if having 4 walls makes it want to blow over like the walls are like a spinnaker sail.
Yeah.
Or having no walls makes the roof want to fly off like an airplane wing. Or if having some partial walls throws everything out of whack.
Yeah, so the code has, it has, I think 3 or 4 categories for enclosure. It's enclosed, partially enclosed, open, and partially open.
Yeah.
Each one has a specific definition. So
partially enclosed and partially open to the layperson's like that's just taking the glass half full, half empty, and giving them different checkboxes.
Yeah, and I'd have to look up partially open, but I can tell you that the enclosed has to do with like the windows on the front of the building and the windows on the other 3 sides. And so like if you think about your typical, I used to use I don't know why, but a lot of your big box stores, they have a lot of glass on the front, and I'm trying to think of a good example, but you really, most of your like Dollar Generals or you know, I guess that's more of a small box store, but same point. It's got a lot of glass on the front and almost no glass on the other 3 sides. And so the wind goes in there and it has nowhere to go. That's the basic premise of it. And there's a formula for that. And
so is that like pop the top because you've pushed it in?
Yeah, so it's a positive pressure.
Okay.
So it's 55% positive or negative pressure. And I say 55% because there's what they call so with wind loads are what they call a velocity pressure.
Yeah.
And so a velocity pressure is like, the best way I can explain it is, you know, you're riding down the road and you put your hand out the window and you feel that pressure. Yeah. So that's like the velocity pressure. It doesn't, I say that example, but it really doesn't actually exist anywhere because the pressure really doesn't happen until it hits something. Yeah. So, but it's sort of a theoretical pressure. And so of that theoretical pressure, what percentage, a lot of it is based on percentage. So internal pressure is 0.55 plus or minus. And so I think about like a soccer ball. So it's pressing on that like 55% of that velocity pressure, let's say 30 psf. So if it was 30 psf, then half of that is pressing either on the soccer ball, pressing it from the inside out, or it's sucking it in, right? So it could be one or the other. So if it's pressing on at 55%, and then on top of that you have another, I don't know, pounds per square foot of 55%, well, that's going to be the full 100% of the 30, so that's going up. So uplift is created through that positive pressure and then the negative pressure on the top of the roof, which is like creating an airplane wing. I don't know if that helps at all, but
it does. Thanks.
Yeah, so you have, I like the soccer ball analogy because the internal pressure really doesn't affect the main wind force pressure of the building, like the lateral, because what happens is, this with the soccer ball analogy as an example, it doesn't matter if it's 100 psf or 50 psf, that soccer ball is standing still.
Yeah.
Because it's got internal pressure on it.
Yeah.
But when I put external pressure on it, that's what makes the pile move left or right. So that's kind of an analogy of internal pressure versus external pressure. External pressure on that ball would be like the wind blowing over the ball and doing something to it.
Or foot.
Yeah, or a foot kicking it. So, so that's, I guess, a primer on internal pressure and enclosure. Partially enclosed would be the typical example of like the big box store. Enclosed would be a typical house that's pretty balanced.
Yeah.
Or a building that's pretty balanced in terms of windows and doors. And what the idea is that the windows are going to break because of impact and missile, even though that is another factor, because now they're requiring us to protect all the windows. And if it's impact glazing, technically it's not considered an opening for wind, right? So that takes that window out of the equation, like the literal equation for enclosure. So it's like it's not even there. So that's one way to eliminate the partially enclosed aspect. But yeah, it definitely increases the internal pressure, which kind of blows the building up theoretically from the inside out. But it's something we just designed for. So I don't know if that helps.
Nice. For just general code design criteria question.
Yeah.
What artificial intelligence have you found is the best one to quickly find needles in haystacks when you're looking for codes? I've tried some, but you think it's getting you there, but they get it wrong a lot.
Yeah, ChatGPT hasn't been a good one for me on the code aspect. It's been okay.
Yeah.
I found Perplexity to be a little better.
Okay.
I don't know if you've tried that one out.
That's my takeaway from this.
So,
Perplexity.
Now, I will say my trick of the trade is, well, I would not use it to design a building, that's for sure. And I found that to be like, I've got a quiz I do with my new hires, and one of them is like a simple beam calculation, and I know the answers to it because I've sent it out so many times. And I had ChatGPT do it, and it actually got it wrong. And it's a simple equation, in my opinion. Three basic questions. So I wouldn't do any calcs with it yet.
Okay.
It's not ready for that. But as far as finding a code provision, it's very efficient at that. And you can always go to that code section yourself in ASCE or whatever and do the research, yourself or whatever. And like, for example, I was doing a little project at my house, and I just said, what is the handrail requirements for like, and it said, I don't remember it offhand, but it gave me the height of the handrail and the spacing, and I was able to pull all that up. And then I told it, and by the way, provide me the links to validate that. So that's the trick, is tell it to provide you some links or some validation references. So
yeah, I feel like it gets, ChatGPT at least gets IBC and IRC mixed up and picks and chooses whatever version and gets the versions mixed up, because you said earlier it's changing every 3 years.
Yeah. So those are a couple of things I've learned. Any other structural questions?
No, that was my last one for you today.
So maybe I could come over and do a lunch and learn with you guys if you'd like, and go over some more things.
Love that.
Okay. All right. Thanks, Jay.
Thank you, Andy.
Take care.
Appreciate it.
Hey everybody, thanks for listening to today's episode of EHANCE, and please do like us,